difference between sulfur hexafluoride and argon gas here. So here the sulfur hexafluoride was increasing in size because gas was actually distributing itself into the balloon and getting into here. So you may have seen the videos where different scientists have put in different gases into balloons and saw that there was this really strange phenomenon that is happening where the gases are actually diffusing either in or out of the balloon depending on the properties of the gas. So there is this video called The Curious Case of Xenon Balloons, which is through periodic videos. And so here in this particular case, this group of scientists had to empty some old containers of their noble gases because of the rent to rent out those containers. So they said, okay, we'll just make balloons out of them and just do some random tests on them. But one of the issues when they did this was they noticed that some of the balloons were losing their gases much more quickly than others. And so here would be 4 examples of the gases that they use. So here we have nitrogen gas, or N2. Then we have the noble gases, neon, krypton, and xenon. So what was happening here was originally they were filling up the balloons to this pretty much the same size, and they were testing to see how quickly they fell down, which was a demonstration on how dense these gases were. Now, what really surprised them was when they did this and they came back the next day, some of the gases actually ended up leaking out of them, which is something that normally happens with gases, and normally we're dealing with it with helium gas, but in this particular case they're dealing with the other noble gases and nitrogen. So one of the issues here that this particular scientist had brought up was he would have assumed that the smaller gases, the gases with the smaller atomic nuclei, would have diffused much more rapidly because they are smaller, and therefore smaller things tend to move more quickly in the gaseous form. Smaller things tend to travel more readily through Brownian motion. They can move farther. So he assumed that the smaller the atomic radii, or the smaller the atomic nucleus was, then the faster it would diffuse out of the balloon. But that was not the case at all in this particular demonstration. So here we could see xenon was actually extremely able to come out of the balloon, whereas neon, which is the smallest of the noble gases that were described here, this was actually the best noble gas to stay in the balloon. And nitrogen gas actually is a little bit larger atomic mass than neon is, but nitrogen gas was actually the best out of all of them at staying within the balloon. Now, granted, the atomic radius of nitrogen gas is pretty much the same as the atomic radius of neon, if I'm remembering all of that correctly. Regardless, nitrogen was significantly better at staying within the balloon than neon was. So that was one of the situations that happened where the gases were leaking out. However, Cody's lab also did a demonstration with sulfur hexafluoride. And so for those who are not familiar, sulfur hexafluoride is a gas that has a sulfur atom and then 6 fluorine atoms that are surrounding that original sulfur atom, and as a result you have an extremely stable nonpolar molecule that is a very stable gas. And so this has a lot of really interesting applications. One of them is that it is such a dense molecule. It is so dense that it can be used for various applications where you want to have a very dense gas. But he noticed the exact opposite problem, where sulfur gas was actually staying within the balloon, but he had the opposite problem, where the gases on the outside of the balloon ended up diffusing into the sulfur hexafluoride gas within the balloon. And so here you can see the difference between sulfur hexafluoride and argon gas here. So here the sulfur hexafluoride was increasing in size because gas was actually distributing itself into the balloon and getting in here, whereas with the argon gas, that was actually predominantly leaking out. Now, granted, there was also gases that were diffusing into this argon gas balloon. However, the net change was more argon gas was leaving the balloon than the atmospheric gas entering the balloon. However, with the sulfur hexafluoride, it appears as though none of the sulfur hexafluoride was actually leaving, whereas the diffusion into the balloon was still happening. And so after a while, the sulfur hexafluoride balloon ends up growing so much that it ends up popping. So there you can see it popping right there. So what is going on here? Because this cannot just be the properties of the balloon itself, or just the size of the gas molecule itself. There has to be something more. So what I basically boiled it down to was these three characteristics are probably playing the most important role. So one, the size of the gas is in fact playing an important role. So smaller gas molecules truly are able to travel much more quickly through the air. They're able to transport themselves much more quickly through liquids and fluids. When they are dissolved in the fluids, they can, just by random scattering, they can find themselves being able to travel much more quickly and much more further. However, that is not exactly the case as what happened here. So that's one thing that can cause it. The other one is the size of the pores in a material. So all of these materials, they are not, or how do I phrase that? So the pore size, or the average distance that is in between the different molecules, or I should say within the different sections of the material, there can be small little holes in all of them. And so this is actually exploited in biochemistry very frequently, and I'll touch on that a little bit. So that is another issue that can cause certain materials to actually flow more quickly or more slowly. And then the third property that I can think of is the chemical interactions between the gas, and I forgot to finish this, but the gas and the material that it is trying, or the medium that it is trying to traverse. So if there is a very strong chemical interaction, that could also be a double-edged sword. One where it could help allow the material to, or allow the gas to dissolve or adsorb or absorb into that material, and the other situation where if it interacts too well, then it can get stuck in that material. So without further ado, let's talk about the size of the gas. So with the size of the gas, you have multiple things going on. So you have Brownian motion, and I cannot just right-click Google when it's like it. So Brownian motion, this is the erratic movement. So with thermal energy, you have materials that are always jiggling around, and this jiggling is not going to keep particles in the same place for very long. What happens is, over time, they are going to move further and further away from their original starting location. And so let's see if Wikipedia, so here Wikipedia has a very good demonstration of what Brownian motion is like. So here we have some random particles that if they have a starting location, you can see their trajectory is moving them further and further away on average from their starting location. Now granted, if you have a small box like this, eventually it can come back to its original starting location, but in general they are moving further away from their location, and that distance will be related to the size of the molecule, and it will be related to the square root of the amount of time has elapsed, if I am remembering that information correctly. So here we can have example of different materials. So this, let's say that this T2 double prime, you know what, I'm not going to go over it that much. Yeah, actually I will. So here this T is equal to 2 double prime, or 2 inches. This would be one example where you have a very light or a very small molecule that is bouncing around, and it is able to travel far, and it has this very wide distribution of where it is located at in a very short amount of time. However, this, where T is equal to 0.1 inches, this was not able to transfer very long in that particular amount of time. And so you have this much more stiff, or this much more localized distribution of your material's concentration, which in this case would be a gas. So this could be the difference between, say, helium and xenon, but this is in a gas. This is where there is very, very, very little interaction between the molecules, or the atoms that are bouncing around, and the medium that it is in, because gas has very little interactions between each other, between the other gas molecules. The only interactions they really have is when they collide with one another and then they bounce off of it. That's basically an ideal gas, but that also is, for all intents and purposes, true for normal gases. So let us continue. So we have the size of the gases, and heavier gases do in fact move more slowly. So this would indicate that large molecules probably would move more slowly. And in fact, in this particular case, this nitrogen gas, which is larger than neon gas, although nitrogen is located close to, or I should say relatively closer to neon on the periodic table, this nitrogen 2 gas is larger than this neon gas, and it is being held better in the balloon than neon is. So what else could be happening in this situation? So the second thing we need to worry about or consider is the size of the pores. So pore size is actually a double-edged sword. So if there was, say, only one size pore in your material, we could easily assume that the small particles would move more quickly than the large particles. So small pores, or I should say, if you have the same size of pores throughout a particular material, and let's say that material was the rubber or the latex in a balloon, what would happen over time is that you would basically just have the same Brownian motion that is happening within the pores of the balloon. Okay, so that could theoretically happen, and since Brownian motion is associated with pores or associated with molecule size, then the smaller molecules would in fact be better at traversing the balloon's material. But that is not what is happening in our demonstrations, because as you can see here, the larger xenon molecules were able to move much more quickly. So what is happening here? Well, this is something that we all need to consider, is that there is never, in nature, there is almost never just one pore size. There is almost never just one size of caverns that exist in any type of matrix in nature. So when we are dealing with rubber, it is very rarely going to be just one size. And so this is actually going to create the exact opposite effect. So in biochemistry, we have a technique called size exclusion chromatography. And so let me get that up for you. So size exclusion chromatography would be when you have a material with a lot of different beads inside of it. And so when you have these beads, I should say, in biochemistry, we often really need to do a lot of separations of the biological material that we are working with. And the reason why is because since biology is such a really messy field, we need to separate things from each other in order to get the material that we want. Okay? So when we deal with size exclusion materials, there are actually, when we do size exclusion chromatography, we use these beads that actually have different pore size inside of them. And so what is the benefit of doing this? Well, what happens is these large molecules are not able to fit themselves into the small caverns of these beads, or the smaller caverns of these beads. However, they are able to flow around them. Okay, so here we can see an example where larger molecules don't go into all of these little crooks and crannies of these size inclusion particles, and in fact they just flow around them, and therefore they actually have less distance to travel. So here Brownian motion is still playing a very important role. Well, in this case it's Brownian motion, and then on top of that there is also going to be the directional flow of the fluid itself. But let's keep on going. So here we have some Brownian motion that is separating these molecules from each other. However, these small molecules have more distance that they have to travel. They have more nooks and crannies that they have to go into, and therefore they're actually slowed down significantly from the normal flow of the material, or the normal flow of the fluid that they are in, whereas these large particles literally just flow around them. And so we could presume, or we could definitely see the situation where larger molecules, if they are not so incredibly large that they can't get through the material at all, if they are able to, they would be able to use the larger pore channels in order to just leak out very readily and not get stuck as easily. So that is one of the things that at least biochemists frequently use, and that might also be one of the situations that is happening here, where the latex and the rubber of the balloons are not going to have a singular pore size, and therefore they're going to have a distribution of what gases, or I should say different size gases, are going to flow or interact in completely different rates. So that is one of the things that can happen here as well. So the third thing would be the chemical properties of the material and the gas itself. So the periodic videos actually made an extremely important point looking into a very old literature that was over 100 years old that described that rubbers were actually, that some of these noble gases, the larger they are, the more readily they were able to absorb into the rubbers, because larger molecules, or I should say larger noble gases and larger gases in general, they are going to be more hydrophobic. And I should say the larger the atom is, if it is at least in the same column of the periodic table, the larger the atom is, the more weakly bound the outer electrons will be to the nucleus. And as a result, as you move, and actually let's just look up P table. So here we have an example of the periodic elements, and let's go to the orbitals. So with all of these periodic elements, as you move down more and more rows, you can see that the atomic orbitals that are describing the outermost electrons become more and more complex, but they're not just becoming more complex, they're moving further and further away from the central nucleus. And as they move further away, what's happening is all of the electrons that are beneath it and below it, they're actually canceling out more and more of the positive charge that is in the nucleus. And so by the time you get to the outer nucleus, you end up having weaker and weaker interactions with the nucleus because all that positive charge is being canceled out by the negative charge of all those electron orbitals surrounding it. And so once you get to the very outside, you end up having more loosely bound electrons. And what is happening with those more loosely bound electrons is that they are able to be manipulated, and they're squishier. They're able to be squished into different configurations much more readily than the smaller ones. And so here we can see an example. Here is neon. Neon is very small, and it does not have a very good ability to be squishy. And here, fluorine, I should also say, is even worse at that. And then we also have nitrogen, which is also very small. So this nitrogen, since it is so small, and since it is this far up, that might be one of the contributing factors to why nitrogen gas might be even better at resisting being floppy. And what I should also mention is that this floppiness will increase the hydrophobicity of that particular gas. And then, therefore, it will allow that gas to dissolve into hydrophobic solvents much more readily. Okay? So this ability to dissolve, or I should say, like dissolves like, right? So the more hydrophobic your gas is, the more likely it is going to dissolve into a hydrophobic solvent. And rubbers, very similarly to other, I should say, the distinction between solids and liquids, as far as how gases will dissolve into them, that's on a spectrum, right? It's not going to be exactly one versus the other. They're all going to have some level of being able to dissolve gases. And if I could give another example, there is a pretty serious situation where hydrogen gas, if it is stored in improper containers, improper metal containers, normally metal is actually very good at preventing gases from penetrating them, because gases have, most gases do not have metallic bonding capabilities. They do not have, how do I phrase that? They have a completely different set of chemical properties that do not normally allow for metallic bonding, which is metallic bonding is when you have the outer most electrons basically liberating themselves from the rest of the nucleus, and those outer electrons are free-flowing around a lattice of these positively charged ions. Okay, so that is the metallic bond. So most gases are not able to participate in that. However, hydrogen gas is. So hydrogen is basically a gas, for lack of a better word, it is more like a very gaseous metal, and it can actually be turned into a metal under extreme pressure under extreme pressures, it can turn into a metal as well and participate in metallic bonding. However, you do not even need those extreme pressures. Hydrogen gas will be able, with some metals, be able to form metallic bonds with other metals. And so the formation of these metallic bonds could in fact be viewed as a dissolving of the hydrogen gas into those metals. And as a result, hydrogen gas can actually corrode and affect the integrity of a lot of metals, and then also presumably you would be able to escape the metals once it gets onto the other side of their containers. Okay, so hydrogen gas is able to do that because it shares similar chemical properties. And so when we are dealing with these gases, and if we're dealing with gases in rubber containers, this neon is going to be much, much, much less hydrophobic than xenon is. Okay, so as we get larger and larger, the xenon gas is going to be much more hydrophobic, have a much squishier outer electron shell, and as a result, it is going to be able to dissolve into rubber much more readily. Okay. So what I should also mention is in biochemistry, we frequently use xenon, or I don't know if we still do this anymore now that technology has improved significantly, but xenon gas was previously used in order to stabilize a lot of proteins so that we could take electron, or I should say, so that we could do X-ray crystallography on them. So what xenon was actually able to do was a lot of proteins and enzymes in your body. The outermost area of the proteins is usually very hydrophilic, so it is able to interact with the aqueous environment of the cell or whatever organism that it came from. But the inside of those proteins, there's a lot more hydrophobic amino acids. There's a lot more hydrophobic components on the insides of those molecules, and that's one of the reasons why the proteins actually have their shape. The protein will actually fold to have more of its hydrophobic amino acids tucked away in this inside of each other, sort of like how oil particles will coalesce into the same little droplet. That same mechanism is happening with the proteins as they fold into their final tertiary structure. Now, the problem is a lot of these proteins can still be very floppy, and that prevents them from crystallizing very readily. But we have often, previously, we used to use a lot of xenon in order to stabilize those proteins in a particular conformation. One of the reasons why is xenon is very frequently able to tuck itself into some of the crevices of the proteins and stabilize particular conformations. And so a lot of protein crystal structures that you will find on the protein data bank will have xenons that are just randomly put inside of it, and that is the reason why, because xenon is a hydrophobic molecule or a hydrophobic gas, and it is able to get into the nooks and crannies of these hydrophobic compounds. Okay, so that is that. So what's the difference? So with this particular video, the larger the molecule that we had, and xenon, the xenon's atomic mass, xenon gas atomic mass. So xenon's atomic mass is 131.3, whereas sulfur hexafluoride's atomic molecular mass, this is 146 grams per mole. So sulfur hexafluoride is actually very similar in size to xenon, right? Sulfur hexafluoride, probably very similar in size and mass to xenon, in fact, a little bit bigger. Why did sulfur hexafluoride end up resulting in the balloon getting larger rather than getting smaller, as is the case with xenon? So this is what I'm going to tell you. The fluorine, I should say xenon, is more hydrophobic because you basically just have this one tiny nucleus, and then you have all these shells of electrons that move further and further out, right? So that is going to be xenon, where the electrons are very far away and they're actually very squishy and very loosely held. It is the exact opposite when we are dealing with sulfur hexafluoride. So sulfur hexafluoride, so fluorine, let's go to the properties, and let us go to the electronegativity. So electronegativity would be a way to quantify how incredible or how strongly an atom is able to hold on to the electrons that are around it. And so fluorine has an electronegativity of 3.98, and xenon actually only has an electronegativity of 2.6, right? And granted, I think that this is the electronegativity of being able to grab a new electron, but I forget a lot of these. No, I think electron affinity is that. So fluorine, yeah, so fluorine has very high electron affinity. So regardless, this fluorine has very, very, very high electronegativity, whereas xenon does not have the same amount of electronegativity. So what ends up happening is fluorines, and let's go back to the sulfur hexafluoride. Caps lock is on. Let's go to the Wikipedia page, might as well. So this is sulfur hexafluoride. So here we have our sulfur, and here we have our 6 fluorines. These fluorines are actually going to hold on very tightly. They're all stealing, basically they're stealing 1 electron from the sulfur, and they're holding it very tightly to the fluorines. And so one of the things that's going to happen is all of these fluorines are going to have a partial negative charge. Now granted, the molecule as a whole will have no discernible dipole, but they will all be just a little bit negatively charged because fluorine is pulling those electrons away from the sulfur. But not only are they doing that, they're also going to hold those electrons extremely tightly close to this very small nucleus of fluorine. And also it's, like I said, it's electronegative, so it's going to hold on to them very tightly. And so as a result of this, fluorine is actually not going to be able to participate in those same electrostatic van der Waals forces that xenon will be able to. Sulfur hexafluoride will be better, could be better seen as like a perfluorocarbon. So perfluorocarbons are not able to dissolve, or I should say, they're not able to participate in either hydrophobic or hydrophilic interactions very easily, because the fluorine, there's no very strong electrostatic interactions that is going to be happening either way. So in the case of sulfur hexafluoride, these fluorine atoms are going to hold on so tightly to their electrons that they are not going to participate in those effects. So going to this, so what is the difference? So why are we experiencing these differences in the balloons? Xenon is large, it's a heavier element, and generally the outermost electron distribution wave functions will be squishier. Therefore, it will dissolve more readily into the balloon material, and as a result, be able to cross that entire barrier much more readily. Okay? The fluorines in the sulfur hexafluoride are the exact opposite. Fluorine is very electronegative, and it has a very small atom, and they're going to hold onto the electrons very tightly, and as a result, even though sulfur hexafluoride is about the same size as xenon, it is not going to be able to dissolve or move through the pores at all. So in this particular case, it's almost as if, when it comes to diffusion, it's almost as if you have a vacuum in the middle of the balloon. And therefore, all of the molecules, all the gases that are bouncing around on the outside of the rubber, if they are able to penetrate the rubber the same way that they are able to diffuse out normally. So the nitrogen gas, the oxygen gas, the argon gas, that can all penetrate into the balloon and penetrate out of the balloon. And since there is none of the gas in the original sulfur hexafluoride balloon, so if we go here, there is none of this gas inside of this, they are able to penetrate the balloon and diffuse into it without any issue. And that is also what's happening with all of these balloons. However, the net change is generally shrinking because the concentrations of these, well, for one, the balloon is squishing down on it, and that is somewhat increasing the pressure inside versus the outside. And so that is actually going to drive a lot of the molecules out, and there's going to be a net driving out. But we don't have that with here. What's happening here? We have that same diffusion. However, as these molecules diffuse in here, they feel like they're in a vacuum almost. The sulfur hexafluoride is playing very, very, very little role in interacting with any of those molecules, and they're playing very little role in allowing, or I should say, they're not escaping the rubber at all. And so over time, you have diffusion of the gases from the outside on the inside, and they're also diffusing from the inside to the outside. However, since the concentration of those gases is so small, when they're diluted by the sulfur hexafluoride, they can't even escape that easily because they're just bouncing around in a lot of empty space, or I should say they're bouncing around in a lot of in another material that is blocking its ability to escape as readily. So that is basically, and 30 minutes, yeah, I think that's pretty much all that I wanted to say. So if we wanted I should say this, I like what this professor had talked about, was that no matter how much you learn, and he's obviously up there in age, and he's a professor at, I believe, Oxford. He's somewhere up there. Regardless, he has spent a very long time studying chemistry, and there's always another paper, there's always another variable that you need to consider. And so what I like to view this as like a black swan event. So for a long time, we didn't think that black swans were a thing, but after we discovered one, then it's like, obviously, the black swans are possible, and why did we ever think that they couldn't exist? The same thing is happening with variables in science, or variables in any type of scientific pursuit. Is you might be able to generate a very good model to understand the world around you, but very frequently there will be another variable that you just have never considered before, because your previous models were very effective at modeling the world around you as far as you were concerned. But the moment that you run into situations where your model no longer fits the reality, or no longer fits the observations that you are making, well, you can discover a new variable that was obvious, and one may argue it was self-evident the entire time. However, if you never ran into an experience that would show you that why, or show you the reason why that variable should have been considered in the first place, you would live the rest of your life without ever worrying about that black swan variable. And so these black swan variables are extremely important in shifting scientific paradigms, and shifting the way that we move from they're just very large changes from one school of thought to another school of thought, when we have this another variable that we need to consider that we hadn't considered before because there was no reason to. Like, we never ran into the situation where we needed to consider this additional variable, but now that we have, oh shoot, well, that was always there. It was self-evident, and it was always something that we should have considered, but lo and behold, we didn't. So that's why we should always, approach scientific inquiry with a large level of humility, because we can always be surprised by what can be discovered. So with that, I think I'm going to head on out. But thanks for watching, and hopefully I will see you later today.